This is Sir Francis Galton, grandson of Erasmus Darwin. In one of his experiments, he measured number of years added to lifespan of clergy and royal family because of people's prayers, and ironically, got a negative number. But today, we are interested in another work Galton did. Galton hypothesized that genius was hereditary. He looked at the high-ranking Englishmen in science, monarchy, and society to see if they were all related. He was also passionate about the statistics. He published his results in 1874 in a book called Englishmen of Science. He published another book, Hereditary Genius, 5 years after Mendel published his Hereditary Genetics. But what does make a distinguished scientist? What are the differences between attributes and productivity of an eminent scientist and an ordinary one? In this video, we'll try to answer these questions and many more. Now, why does this matter to you? In our first video, we discussed Dunning-Kruger effect, where we overestimate our competence and how well we are doing. We looked at MacArthur Wheeler, a bank robber who wore lemon juice to make his face invisible, but got arrested because his photo from the bank cameras was published. Yet, he could not believe it. He lacked metacognition, the ability to realize whether the strategy or actions will succeed or not. One conclusion Dunning and Kruger made was this: the most effective way of obtaining better metacognition is to learn theoretical knowledge and practical skills. So this video builds on earlier videos to provide us with knowledge and understanding. I also suggest you watch that video after you watch this one. Now, back to Sir Galton, father of fingerprinting. What did he count? He studied men in human affairs and science. He measured eminence using criteria such as being recently mentioned in 2500 Men of the Time or in the Times obituaries. He noticed 1 in 2000 men were eminent, while it was 1 in 20,000 for general population. For scientists, however, the eminence threshold was having 2 or more of the following criteria: membership in Royal Society, having a university chair, medals or awards presented by a learned society, holding an office in such societies, or membership in an elite scientific club of academic worth. Among all eminent men, he counted 10% active in science, leading to 1 eminent scientist in 200,000 people. His generosity in counting was to compensate for the ones he overlooked. But Galton conducted his study in 1800s. Did the numbers change since then? In 1903, James McKim wrote American Men of Science, which is still in print as American Men and Women of Science, summarizing biographical information of American scientists. Cadell started with 1,000 names and added a constant number each year. There were 11 eminent names per million in the first edition. In 1938, it was 12.4. This is while the number of scientists and the scientists per capita were doubling every 12.5 years and 17 years, respectively. The reason for this stable density could be that Cadell used a different criterion for distinguishing eminent scientists, or the 1,000 name quota and constant annual increase were out of proportion to reality. But main reason seems to be that his definition of eminence was a rigid yes or no answer, independent of time and distribution of scientists. A scientist may be elite but not recognized. This is equivalent to drawing a line on the IQ distribution and never moving the line. The proportion of people above the threshold is always constant with time. Now, how can we define a criterion that is not a yes or no question? We can measure an acceptable index for each scientist and look at its distribution, but this index must be correlated to eminence. We will start with publication count and first we'll justify it. We can argue that this index is not good because it incentivizes scientists to increase the quantity rather than quality of their publication, but eminence is highly correlated with productivity. For example, Wayne Dennis looked at National Academy of Science biographical memoirs between 1943 and 1952 and found that among 41 men who lived past 70, their publication count ranged from 768 to 27. The average was 200 papers, with 15 members having less than 100 papers. Similarly, among Royal Society members of 1800 to 1900s, he found that top 10% had over 50 papers and half were featured in Britannica for their distinguished work. Of the top 5% with more than 140 papers each, 70% were in Britannica. None of those mentioned in Britannica had fewer than 7 papers. Now, how can we use publication count as our criterion? We can go to Web of Science and compile a list of authors who published in a journal and count how many times they published there. Then we can plot the distribution. Number of authors, n of n, who have n papers, with n equal 1, 2, 3, and so on. This is what Lotka did in 1926 on Auerbach's Geschichtstafeln der Physik and Chemical Abstract. He found that the distribution of productivity is what we know as Pareto distribution. Here, C is the frequency of single paper authors and A is a constant. For Auerbach's and Chemical Abstract data, A was 2.021 and 1.888 respectively. We can use the distribution to find the total number of scientists in the field and the average number of papers per author, just by knowing total number of papers. Pareto distribution of wealth is a special case with A equal to 1.5. We will discuss Pareto distribution of income in future. Subscribe and tune in so you don't miss it. Special case of A equal 2 is called inverse square law of scientific productivity. For simplicity, we will call it Lotka's law. It implies that number of authors with 2 papers is quarter of single paper authors, and so on. Analytically, assuming highest publication count is infinity, we see 60.79% of authors publish only 1 paper. For our data, 59% of authors published only once, and A was 1.87. Note that we didn't account for author's position in a multi-author paper and number of authors per paper. Shockley showed that single-author papers follow a similar distribution. He ranked the scientists based on number of their publication and plotted logarithm of number of publications as function of rank. He found that those who had solo papers were also collaborating with many others, contributing to idea formation and development, a key aspect of eminence. But even correcting for the number of authors per paper, the distribution remained consistent. It seems inescapable. Lotka's law implies that science does not fall from heaven through random processes. Productivity depends on multiple prerequisites, so we should not expect to get Gaussian or Poisson distribution of productivity. It also gives us price square root law. Let's say we have 100 authors and we rank them based on number of publications. Let's also assume that the top ranking author has 144 papers. Then, according to Price's square root law, top 10 authors publish 50% of the papers, and their lowest publication count is 3/4 of the square root of 144, 8 papers. This gives us an immediate measure of eminence. Square root of total number of scientists are eminent scientists who do 50% of the work, and least productive among them produces 3/4 of a square root of what the most productive among them produces. Now let's apply Price's square root law to our data. We see that out of 74,509 authors, the top 273 authors produce about 11% of the work. In fact, we are not the first ones to try this. Nichols already showed that Price's square root law does not fit neither empirical data nor the simulations. Now, is Price's square root law wrong? Price himself admitted that Lotka's law needed modification. This was because Lotka's distribution did not limit the largest score. For the cumulative distribution, number of authors who have P papers or more, Price recommended A times K divided by P times A plus P. with A and K as fit parameters, instead of number of authors times single paper frequency divided by number of papers. He used this distribution to fit it to Lotka's data. For authors with less than A papers, this distribution is approximately K divided by P. For those who have more than A papers, the distribution is approximately AK divided by P squared. AK is the total number of authors. 10% of them have 10 papers or more, and 1% of them are highly prolific at the level of National Academy of Science. In Lotka's law, a problem with its interpretation and application, Price and his objectors showed analytically that we can derive Price's square root law from Lotka's law, albeit with few extra assumptions. There, Price stated the general form of his rule, that there is a score M for which half the papers are published by authors who have M papers or more. Price assumed that the largest score was the number of papers at which there was only one author who published more than that. This was a valid assumption because Lotka's law does not really apply to highly prolific authors who are scattered here and there at the end tail of the distribution. We will not look at the proof, but the link is in the description. We can always use the general form of Price's square root law, that a small proportion of authors do major proportion of the work. When we use the 90-10 rule, 10% do 90%, or 80-20 rule, we basically are indicating a very specific distribution with a very specific exponent. Now, why does a small proportion do majority of the work? There was an experiment that showed this difference in productivity. 3 litter-mate rats were trained to push a lever on one side of a cage as their job and receive food on the other side as their salary. When all 3 rats were placed in the cage, they did their job, but when one pushed the lever, he never got his reward. Other rats got the reward in his stead. They kept doing what they were trained for, not getting what they meant to. So hunger built up to the point that they showed aggression and frustration towards the bowl they got food from. But that did not help until one of them started to show aggression towards the lever. He pushed the lever so many times that the other 2 were satiated. And the third rat, the hard-working hero, finally managed to receive the reward he deserved. In the end, productivity graph showed the disparity among the rats. The disparity in productivity was the natural response of the biological system. As we mentioned, productivity, creativity, and success have multiple prerequisites that are not independent and random. They derive the result non-linearly. We can see this non-linear process, for example, in Lotka's law, where the cutoff score is not the mean or median, but 3/4 of the geometric average. Furthermore, we, the scientists, all intuitively know that the effort to go from 1 paper to 2 papers is the same as going from 100 papers to 200 papers, and not the same as 100 to 101, as the layman may think. Fechner-Weber law in psychophysics, a field founded by Ernst Heinrich Weber, describes the relationship between a perceived change in a stimulus and the initial one. Gustav Fechner, Weber's student, refined this law by providing a mathematical formulation showing that perceived change is inversely proportional to the initial stimulus. Mathematically, delta P is proportional to delta S divided by S, where delta P is the change in perception, delta S is the change in the stimuli, and S is initial stimuli. This equation will give us the logarithmic relationship between perception and a stimuli, like light or sound. P equals K times log of S divided by S0. Now, if we take the number of papers as a stimuli, the perception of effort is a constant times logarithm of new number of papers divided by initial number of papers. In this sense, logarithm of 2 divided by 1 is equal to logarithm of 200 divided by 100. At the same time, the more we practice something, the better we get at it, making it effortless. So persistence and perseverance are the qualities of the successful. Now, Shockley found that logarithm of number of publication has normal distribution. He argued that the ability of individual to keep multiple ideas in mind and realize the relation at the same time is the reason. For example, the person who can keep two ideas in mind has two combinations to invent, but the one who can keep three ideas has 6 ways of producing inventions, and this makes him 3 times as likely to produce. Furthermore, he argued that productivity requires multiple independent attributes that are multiplied to give the final productivity prerequisites. So a small variation in one or more can result in a huge advantage for the individual. But what are the attributes that correlate with productivity? Higgins and colleagues show that IQ, dorsolateral prefrontal cognitive abilities, and personality trait conscientiousness correlate strongly with high academic performance. Dorsolateral prefrontal cortex is the center for high-level cognitive tasks and executive functions like working memory, cognitive flexibility, planning, inhibition, and abstract reasoning. They also looked at personality traits in Big Five model and found that conscientiousness correlates strongly with academic performance and can predict it on its own. Conscientious people are organized, orderly, and can plan their goals very well and stick to the plan. Jordan Peterson has many great lectures on this topic and explains all the personality traits in details. I left the link in the description. Now, since the scientist, as we have assumed, has a PhD degree, and getting a PhD degree requires a robust academic performance, we can safely assume that scientists have relatively high IQs, high dorsolateral prefrontal cortex abilities, and high conscientiousness. In addition, another study showed that high research performance is positively correlated with openness to new experience, but negatively correlated with social traits, namely extroversion and agreeableness. It also showed that openness and neuroticism correlate with research engagement, which is the measure of how much the researchers enjoyed the research, and the research engagement is positively correlated to research performance, mediating the effects of personality traits on research performance. Research performance was measured by considering the researcher's publication and weighted impact factors of the journals. The higher the number of publications and the better the quality of journals in terms of impact factors, the higher the research performance was rated. Those who have high openness are interested in creative artistic activities. They like art, intellectual and philosophical activities, and can come up with new ideas that they like to pursue. High neuroticism makes the individual more sensitive to negative emotions. A unit of a stressor will cause 10 times more anxiety, fear, and stress in a highly neurotic person compared to the average person. If we use Fechner-Weber law, we see that this constant before the logarithm of a stressor intensity ratio is larger for a neurotic person. So, conscientiousness positively correlates with productivity, and neuroticism's negative correlation with productivity means it reduces research engagement and productivity, for example by preventing the researchers from taking risks. Furthermore, extroverted researchers tend to socialize more and receive positive emotions from socializing, rather than focusing on the research in solitude, which reduces productivity. And if they are agreeable as well, then they tend to avoid standing up for their ideas and arguments, leading to further reduction in research engagement and productivity. This is shown in negative correlation of social attributes with research performance. Lastly, openness to new experiences, in simple words, is the burning curiosity that drives the scientists to find the answers to their questions. So, we can conclude that IQ is not the only determining factor of success in terms of productivity. And to support this proposition even further, we can look at more data. For example, in an experiment in early 20th century, Louis Terman followed 1,470 children with IQs 140 and more for more than 50 years. After 50 years, 20% were clear disappointment and had no successful careers. Some were very successful and some other were average. Among the bottom 150, only 8 received a graduate degree and dozens only graduated high school. Among top 150, 98 of them received graduate degrees, which was 10 times more than the bottom 10%. The disparity among top 1% in IQ score showed that the high IQ did not guarantee success. But the most mind-boggling fact was that among children who were excluded from the experiment for not making the IQ threshold, 2 won the Nobel Prize in Physics, while none of the participants managed to achieve such high level of success. As Thomas Sowell says, and I'm paraphrasing here, you can have an IQ of 170, but if you're illiterate, it is useless to you. Now that we know how Pareto distribution and log normal distribution of productivity are caused, what implications can we expect? Price defines solidness as log of number of publication, which is normally distributed, like IQ. A scientist with 1 paper has solidness of 0, and the one with 100 papers has solidness of 2. Immediately, we can deduce that logarithm of number of scientists with solidness S decreases linearly. Price claimed we could see this constant linear drop in Army's General Cognitive Test normal distribution's tail. Every 11-point increase in AGCT was equivalent to 10-fold decrease in the number of people. But he did not try to provide any other attributes that influence solidness and stopped at IQ. Yes, AGCT measures IQ, but we can consider the distribution of individuals along the combination of influential factors: personality, dorsolateral prefrontal cortex abilities, IQ, and other variables we may have missed to more accurately define solidness. Unfortunately, we need to leave this topic for later. So far, we have established that Lodkow's law of productivity is the result of multiple normally distributed factors, Fechner-Weber law, and Shockley's multivariable model. Now, if we follow Price and only consider IQ, what is the average IQ of a scientist with solidness of 0? In 1958, Harman studied intelligence of 7,787 PhD graduates with average age of 32 years, using the AGCT with a median of 100 and a standard deviation of 20. Average AGCT scores of fields ranged from 140.3 for physics to 123.3 for education. We see AGCT scores on the horizontal axis. The dotted smooth curve corresponding to dotted vertical axis represents the general population's AGCT distribution. The solid polygon corresponding to solid vertical axis represents Harman's sample. The solid curve with this vertical axis on the right shows the number of PhDs per 1,000 individuals of the same AGCT score. Among highest scorers, 175, only 1 in 5 pursued PhD. In our terms, became a scientist. Price assumed that highest IQ made the eminent scientist. Then he argued that to increase eminent scientists 5-fold, the total number of scientists must grow 25 times, from 8,000 to 200,000. He suggested using Harman's average AGCT score of 130 with rarity of 1 in 15 as threshold, allowing about 160,000 individuals from 2.4 million people of the same age group to qualify. Harman's sample showed 1 PhD per 3,100 people of the same age. Right now, in the US, we have 167 million people under age of 32. The threshold gives us 11.13 million scientists. 1.1 million would produce 10 or more papers. 111,000 would publish over 100 papers. This equates to 33,433 ordinary scientists and 334 eminent scientists per million of population as the higher limit. Price's estimation was 400 per million. Both estimations exceed Galton's and Cattell's. But is this limit a hard limit? Can we really increase the density of top scientists by an order of magnitude? Yes, it is a hard limit. Harman's study showed 4 out of 5 potential top scientists are not pursuing science. Price attributed this to lack of opportunities, incentives, access to good schools, and competition. He predicted instead of addressing these hurdles, we would focus on increasing scientific manpower, hoping the number of exceptional ones rise proportionally, a prediction that came true. Reaching this limit is challenging, and pouring every eligible individual into science will come at the cost of other fields, In 2022, 57,000 PhDs were conferred in the United States, representing 9.1% of eligible individuals based solely on IQ, a significant increase from 4% in the 1960s. Notably, nearly half of these PhDs were awarded to international students, compared to just 13% in 1963. But Mortimer Adler teaches us that we are allowed to disagree with an author when he's uninformed or when his argument is incomplete. Price assumed only IQ determines eminence, and the argument that he made was logical, but he ignored, openly admitting it, other factors that make eminent scientists. High IQ alone does not guarantee a Nobel Prize. Perseverance and persistence, characteristics explained by conscientiousness, also play a crucial role. It is probably the case that at most 1 in 5 of highest IQs can become scientists simply because needing 2 prerequisites, each with rarity of 1 in 15, leads to a chance of 1 in 225 to have both. So we can't agree with Price that the other 4 will be eminent scientists or that we need to increase the total number of scientists 25-fold. But at the same time, it is very difficult to determine how much increase in manpower is required due to multivariate nature of the problem. So far, we have seen the proof of proposition we stated in the previous episode, that the science cannot grow forever because the number of people who can become scientists is limited. Now, we can define the solidness of a field as logarithm of number of researchers in that field. For a field with 100 researchers, we get a solidness of 2, and for a field with 10 researchers, we get a solidness of 1. So, which one is superior? A field with solidness of 2 or 10 fields, each with solidness of 1, adding up to a solidness of 10 in total? In last episode, we saw science's law of exponential growth. There are 2 parts to this growth. Science wants to minimize its solidness. It seems that scientists gather in small groups and fields, and the small groups gather in small institutions, and these institutions absorb more groups to become larger institutions, a process of crystallization. Size of the large institutions like universities grows at the same rate that the number of small groups increases. In this manner, giants in the lead will remain in the lead by constantly absorbing small groups and individual manpower. Falling behind and moving backward is an exception to the rule. Usually, the giants stagnate in their mature state until another growing giant who has a higher growth limit surpasses them. We can see this in the growth of cities. In human behavior and the principle of least effort, Ziff ranked the cities based on population and plotted the log-log graph. Over many decades, the slope of the line was constant as the line moved up. This meant that the population of the first rank grew at the same rate as the number of small cities. Cities moved up and down in rank, but to be in the first place, cities had to reach higher and higher populations. The same is observed in the lists of sizes of faculties, number of PhDs per decade of the college scientific departments in any field or in general or in any country. This behavior is also followed by ranked lists of scientific contribution in terms of number of papers, journals, and expenditure of nations of the world. Now, what is the conclusion? About this process, there is the same sort of essential built-in on democracy that gives us a nation of cities rather than a country steadily approximating the state of uniform population density. Scientists tend to congregate in fields, in institutions, in countries, and in the use of certain journals. They do not spread out uniformly, however desirable that may or may not be. In particular, the growth is such as to keep relatively constant balance between the few giants and the masses of pygmies. The number of giants grow so more slowly than the entire population that there must be more and more pygmies per giant, deploring their own lack of stature and wondering why it is that neither man nor nature pushes us toward egalitarian uniformity. Yes, there is a built-in on democracy in the system, and most will be least productive. But remember the rat experiment? we are creating a situation where we have only one lever to elevate them all. That will result in the Pareto distribution of success. It is in our nature to follow the herd. As Carl Jung says, where the many are, there is security. What the many believe must of course be true. What the many want must be worth striving for, and necessary, and therefore good. But we saw that the smartest of us may not make an eminent scientist. By the way, I did not even attempt to discuss external prerequisites like luck. Veritasium has a good video on that you can watch. Some of you may say, oh, I'm failing because I don't have the genes, or I'm not smart enough, or conscientious enough, or I'm too neurotic. To that I say, you are dealt with a hand, and you can find the game you will succeed in it the most, a game that is most meaningful to you. The hand only sets the limit and amount of effort you need to get there. There are many logistic curves you can pick and grow along, some better than the others. Just remember that they won't be the same as someone else's. So do not compare yourself to who someone else is today. Compare yourself to who you were yesterday. You are built for adversity. If you put yourself in new difficult situations, new genes get activated in you that help you adapt. Knowing your abilities and pushing beyond those limits will increase your limits. You just have to keep on keeping on. In short, you can become more conscientious if you practice the habits, plan and stick to it, and clean your room and become more orderly. When I found out I'm in 90th percentile in neuroticism, I realized how much my causeless fear and anxiety was hindering my success. So I routinized my day, eat, read, sleep, and exercise at the same time every day. I stay away from carbs and sugar and stick to protein and fruits. And every now and then, I take some ashwagandha to help with the rush of stress. Doing these, I have minimized the effects of my neuroticism. So, understand yourself, just pick one goal and keep on keeping on, constantly learning from your mistakes and adjusting your aim to reach the top of your curve.
The point is that there's some games you don't get to play unless you're all in. And the other thing that's so interesting about being alive is that you're all in. No matter what you do, you're all in. This is going to kill you. So I think you might as well play the most magnificent game you can while you're waiting. Because do you have anything better to do? Really? Why not pick the best thing possible that you could do? Why not do that? Maybe you could justify your wretched existence to yourself that way. I think you could. That's what it looks like. You know, people find such meaning in the responsibilities they adopt, it stops making them ask questions about what life is for. If you have a newborn, and so then I think, well, if you got your act together, it'd be better for you, and instantly it would be better for your family, assuming they wanted you to get your act together, and not everyone does, and then it would be better for the community. It's like, how far could you take that? If you stopped wasting time, and if you stopped lying, and if you oriented yourself to the highest possible good that you could conceive of, and you committed to that, how much good could you do? Well, I would say, why don't you find out? So that's what I think you should do. You should find out. Because you're more powerful than you think. Way more powerful than you think. I mean, God only knows what you are in the final analysis. You're blind to your own weaknesses, but you're also blind to your own strengths.